I would like to say thank you guys for being here today for this periodic seminar. Welcome back. Today we have the talk by Fernando Gonçalves, PhD student at the Federal University of Santa Catarina in Brazil, with working there with Leandro Baker. Today he has the opportunity to talk about model-driven engineering approach to design sensing and actuation subsystems. We'll have around 30 minutes to entertain us on this subject.
Okay, so thank you for the introduction. So this topic is part of my research on Brazil. I'm working with design of embedded systems, more especially to design unmanned aerial vehicles. So I will talk a little bit about that. This is the outline of my presentation. So this topic is part of the project. This project had started on 2012 on my university in partnership of Federal University of Minas Gerais, and we focus on design of autonomous birotors UAVs. So we aim to integrate the different teams. So we have control engineers, software engineering, and aeronautic engineering also working together to build this kind of aircrafts. We are now composed at least of 18 people, of PhD, masters, and undergrad students. Actually, we have 3, maybe 4 aircrafts. The first one, the second one was built at my university. The third one, it was designed on Minas Gerais, and this one it was building on Minas Gerais also. Here I have a short video of the first aircraft with where we had. Sorry, I think I. So here we can see a flight test with we have a pilot that is controlling just sending the position references to the aircraft. We have altitude control, autonomous, and the guy is making disturbance on the systems to evaluate the stabilization control. And so we have just 2 rotors. It's a different configuration with the traditional quadri rotors, and it's more difficult to control because of that. And so to design this kind of aircraft is not a easy task. So this is the UAV, this kind of applications. It's a typically cyber physical system example. That cyber physical systems, it's a kind of system that, as we know, that combine computational systems with the physical systems, providing the proper control to the specific application. We have today many applications of this kind of systems in the industry, in the autonomous, in the vehicles, in the aircrafts, and in the home and health applications. So basically it's a composition of physical devices. That is my topic research actually, communication systems, and embedded computed platforms in order to make the whole application. So to design this kind of systems, by the use of model-driven engineering practices, we usually make different models, design different models to express the system characteristics, and these models are used to make the real application. So basically, we use, in my approach, we use 3 different models. The first one is used to express the system behavior. We use mathematical models in order to express the system behavior according the control references. So coupled with this model, we design a functional model that's used to specify the control algorithms and the system operational modes. And coupled with the first model, the analytical model, are used to simulate the system and analyze the system behavior according the control approach that we are designing. And in order to support the control design algorithms in the real application, we design a third model that represents the system architecture, where we express the software, the system software, process, threads, and communication systems integrated with the real devices like embedded platforms and the system devices. And these characteristics are represented in the architectural model. So in this topic, we use the Simulink models in order to express the functional model, and the AADL models to express the system architecture. So here we have an architectural model that expresses the characteristics of the embedded platform and also the software structure, threads, and processes. And inside of these components, we have the functional model that express our control systems. So in this way, my job aims to address how to perform the transition from the simulation model, the Simulink model, to the implementation model that we call here the architectural model. And in order to replace the analytical model, the model that express the system behavior to the real sensors and actuators, because we know that the analytical model represents the system behavior, but when we are in the real application, we not have just one model to express the system behavior. We need mainly a set of system devices like sensors and filters and actuators in order to proper control the system and express their behavior according we are choosing to control. So and with this job we aim to provide adequate to support to express these characteristics of the sensors and actuators on the real system. So why we choose the Simulink to express the functional model? Because it's a robust tool and support the design and discrete and the continuous systems, have a big component libraries to support this system design, and provide interface with the embedded platforms like Discovery, BeagleBone Black, and others embedded platforms that we can design directly on the Simulink, and then evaluate the behavior directly on the embedded platforms, and also support the system simulations and analysis directly on the tool. So, and the AADL, it's a textual language to express the architectural models. It's very used in avionic context, but like Airbus use ADL models, and another ones support the specification of software components and hardware components like processors, bus, and power components and integrate these physical components with the software components like threads, process, and these kinds, and functions also, and support different kind of analysis like scalability, flow latencies, and other things that we can analyze directly on the architectural model before to implement on the real application. So this work, it's based on our previous work. It's a work of our group. It's a PhD thesis from Passarini in 2015, where she designed a transformation process between Simulink model to the architectural model. She defined on his process the design of the definition of the system requirements, design the Simulink model, and detail this model with some informations, and then perform a transformation process in order to generate the AADL model and the application, the code of the application. But these transformations, this approach does not comprise the generation of a set of sensors and actuators. In this approach, she assumes that this process can be designed at the future by the engineers and not during the transformation process. So in this way, we propose an approach that aims to extend these previous works in order to allow the engineers represent the characteristics of the sensors and actuators directly during the transformation process, and not need to refactor of the architectural model after this first generation to include these informations. So we define a set of input devices and outputs, the sensors and actuators of the application, and specify the required sensing and actuation functions like filters and other functions that are required to the real application. And organize these functions and devices in a set of software structures, more specifically in a set of threads that will be executed on the embedded platform. So here it's a flowchart of my approach. Basically, we start selecting the block of the Simulink model that represent the analytical model, the model of the system model, and then analyzing their properties. I will explain a little bit more with the pictures of my tool, and finally we perform the model transformation, generating the architectural model. So we use as a case study a birotary UAV. The functional model is composed by two blocks: the control approach and the UAV dynamics. We needed to put some marks on these models, on these blocks. It's because of the transformation we used by Passarini that requires that we mark these blocks to apply the transformation on the tool. So starting our process, we first analyze the blocks of the system and select the block that represents the UAV dynamics in order to replace this block by a set of sensors and actuators in a generated architectural model. So after select this, we start the definition of the actuation subsystem. Firstly, we analyze the system, the block outputs. Basically these outputs are the information that the control system send to the system actuators. So here we can define that it's a single information or it's a vector, that if this information needs some processing or can be directly sent by a specific actuator. If this information can be directly sent, we can specify just here the specific actuator to this information, or mark to create pre-writing functions. If the information needs some, in our case, in case of the UAV, we need to pre-process this information to send to our actuators, and we create a specific function named signal transformation that receive the function inputs, the inputs from the control systems, and provide the forces to our motors and the angles to our servo motors that are responsible to the motion of our UAV. So basically, we specify the inputs and outputs of this function. Based on the outputs of the functions and the signals that not needed pre-writing processment, we define the system actuators. Here we define some characteristics of each actuator, like protocol, communication protocol, priority, and period of each of our signals, and then organize the actuators and functions in software structures. In our case, it has a set of threads according their periods and functions and another characteristics that are required to the system actuators. Defined these characteristics, we finish the design of actuation subsystem and start to define the sensing subsystems. This process is started analyzing the inputs of the selected block. These informations usually cannot be directly obtained by specific sensors, and usually needs to a set of redundant sensors or something, or combine information from different sensors to specify, to obtain in this case the system behavior, the UAV behavior. And here we can specify that the specific input needs a post processing or can be directly obtained by a specific sensor. In our case, in the UAV, we have two functions. One function responsible to interface with the sensors that have a higher response time, and another one to the sensors that have a lower response time. We have one GPS that provide their position around 10 milliseconds, and IMU and sonar sensors that provide a system behavior of the UAV around in each 5 milliseconds. Because of that, we needed two different functions to process this data of these different sensors.
What's IMU?
IMU, it's inertial measurement unit. We have 3 accelerometers, 3 barometers, and 3 magnetometers to obtain to specify the behavior of the UAV. So here we create I put just one, just the function that specify the system behavior, that receive the IMU and sonar sensor data and provide the velocity and attitude and angular velocity of the system. and we have another one that receive of GPS data and provide the position. So based on the signal inputs, we specify the system sensors and their specific protocols, priorities, and periods. And because this fact of we have two different periods, we need a set of two threads, or two software, sensing software.
What does mean priority in this case?
So AADL works also with have a specific a property that is priority. I think it's when you perform the scalability analysis on the directly on the model, he use these priorities to according the specific model of scalability that we use to perform the analysis. I think it's to that we need to specify the system priorities on the threads of the AEDL. So after design the sensing threads, we perform the transformation of generate the AEDL model. Here's the main view of this model. Here we have the control process and another process that is the sensing and actuation that receive the information that we provide during these different windows on the wizard. And here we have a set of devices of the system. So extending the sensing and actuation process model, we can see here a set of threads that are responsible to the actuation and the system and system behavior. And extending one of these threads, we have here the subprograms call that will perform the functions design on the functional model. And here we have a dispatch protocol, period, deadlines. And I don't put here, but we have here also the priorities that was specified during the wizard process. So concluding, with this tool, we aim to support the automated process, the design of the sensing and actuation characteristics, systematize the design of these subsystems, and how we can replace this one model that is an analytical model to a set of system components and software structures in order to make a more complete architectural model more closer to the real application, and integrate the control algorithms, estimation filters, and system devices. As a future works, we are working in designing space exploration techniques to generate more elaborated models, and we are integrating a process to transform the architectural model in a timed automatas in order to perform the formal verifications, and we aim to generate a monitor to perform runtime verification also in the embedded platforms. So I think it's, I don't know, maybe I will talk a little bit fast, but it's mainly this main idea of this process. If they have questions.
So yes, we have room for a few questions.
I have a question. Why do you choose having two motors instead of the usual four ones?
Yeah. So this is an option of the control engineerings. They are choose this specific configuration of the aircraft to have a different from the traditional ones, quadrirotors, mainly because the control challenges, because it's more have more challenges to control just 2 rotors coupled with 2 servo motors, and have and we don't have very much works in this kind of configuration, and because of these things they choose to work with big rotors, and we have works now designed on there to couple these aircrafts with the fixed wings in order to perform to switch the flight modes of the helicopters to access difficult areas, and to the airplane modes with the fixed wing to cover a larger area during the flights. Yeah?
Slight extension of the previous question. Do you think there would be some benefits in terms of like this thing, like instead of 6 or 4 using 2? Do you think there would be some benefits in terms of fuel consumption, the weight? Does it make sense to expect that it would better in this sense? Like
so,
some real life scenario.
Yeah. Without using a fixed wing, we have almost the same energy consumption than a quadrirotor. But using a fixed wing, we can use aircraft mode, and using the aircraft mode, we have less consumption than a quadrirotor, for example. And in this case, yes, we have less consumption than a traditional quadrotors or hexacopters. But I think I know that quadrotors or hexa or octacopters, it's more stable for use, for example, to live cameras or this kind of applications. Two rotors will be more used for scanning a large area or another kind of application that we not need so stable flights, for example. Yeah.
Do you integrate any type of timing analysis in your framework? Because for this kind of application, which are basically controlled, the response time of your control loop is actually very important for stability of your system.
Yeah.
So currently, I've seen that in this framework, we're basing everything on the refreshment rate of the data that are coming from the inputs. What is required by the output, but I suppose the end-to-end response time is also important.
Yes. So this is not directly expressed on the transformation process, but on the AADL models we can express a flow process, a flow of the information. We can specify when, where these information are generated, and how much time do you expend to receive on the end of the flow. And
but wouldn't it, because the AADL model is already quite low level,
yeah,
because you know the architecture and everything, but wouldn't it be interesting to actually express that in the Simulink model already? Because
this is I simplify a little bit this model. This model, it's a simplification of the real model used to analyze the control algorithms. Yeah, in the control, when we design the control algorithms, we express directly on the Simulink models this the time of the information that are produced here, and the times that this information is also produced to the system model. Yeah. It's I don't mention that, but we start with this model that you had mentioned, with more timing and other kind of informations in this model. But to perform the system transformation, to generate the system architecture, we need to generate a higher view of this model with a little bit less information, to provide the system, to generate the system architecture. But we had another model generated before of that included these informations to perform the system simulation on the Simulink before to perform the transformation.
Okay, so I suppose that it would be interesting also to actually use that information to check that your implementation is consistent with your simulation.
Yeah.
So not losing that information through the process.
Yeah.
Maybe write it down in the ADL models and then later on checking it with runtime information that you get during the
Yeah, I need to look how to extract this information to the Simulink model to put directly on the AADL model. Actually, we are doing here on when we generate the system threads, or after that some specific characteristics are included manually on the AADL model based on the previous functional model, more completely functional model. But I know that it's not so good because we can switch this information, or if you have a automated process, it's more you can guarantee that the first model it's really equal to the generated architectural model.
Another thing that would be interesting to do in that case would be that you could automatically configure those parameters that currently you put by hand, which are the areas and priority of your threads.
Yeah. I'm looking for improve the I have I presented this work in EDFA and I received some reviews there and here also, and I'm looking for improve the tool. It's a first version. We need a lot of work to do to make it more useful to the engineering side. I know that, and I will try to improve the tool to make more useful and more automated because it's this topic in specific to integrate the sensors and actuators. It's I have looked for some papers, but sometimes we have papers more focused on the control systems or in the software systems, but in this integration of the real devices to the it's a little bit, I think it's a little bit less explored that, and it's really difficult. We have a lot of experience with designing the aircrafts on the lab, and we spend a lot of time to integrate this kind of devices on the real applications because of this, the less of the expressed characteristics on our models.
Questions?
One last question, but more philosophical than technical. Actually, in the design process,
Okay.
you have the design, you have the ADL model, and then you have the simulating model.
Yeah.
Where do you find more challenges, and why?
On the translation of one to another one, or
Which part is more difficult to derive?
The Simulink model, it's we have just an MEDL file that we have a lot of information inside of that, and the first challenge it was looking for that file and find the information that we needed to generate the architectural model. The another one, it's to express the meta models of the Simulink and the AADL in order to map the transformation itself, and to find these kind of structures can be mapped to this kind of structures. It's a little bit difficult when we work with model transformations. And now I'm working with Davi to transform the architectural model in a time automated automata. And this is another challenge to find some common characteristics that we can extract or include on the architectural model in order to automatically generate another models. I think it's a big challenge to.
No more questions. Let's thank the speaker again.